Started? Okay. So hello everyone, it is my pleasure to welcome Professor Mike Chen from the Department of Electrical and Computer Engineering at the University of Southern California. So Professor Chen, as a graduate student, he proposed and demonstrated the asynchronous SAR ADC architecture. This has been adopted in the industry today for low power, high speed analog to digital conversion products. So in 2011, he joined USC and he leads the analog mixed signal circuit group. And he focuses on data converters, frequency synthesizers, RF and millimeter wave transceiver designs, AI-assisted analog circuit designs, etc. He received the Qualcomm Faculty Award in 2019, NSF Faculty Career Award, DARPA Young Faculty Award in 2014. And his research team has received several other awards such as ISSCC Jack Kilby Award and RFIC Best Paper Award. And he's guest editor or editor of various circuit journals like IEEE Journal of Solid State Circuits. And he has given distinguished lecture at the IEEE Solid State Circuit Society, and he's also an IEEE fellow. And I welcome him to give this talk on high-speed DAC towards high performance and efficiency. Welcome.
Thank you, AJ. Yeah. Thank you, AJ, for the kind introduction and invitation to give this seminar series, I guess. Okay, so I guess I'll get started because I understand we have a time constraint. So today it is my pleasure to share, part of our research topics and being the DAC, right? So we over the past, I think more than a decade, we work a lot on this, I would say high performance, high speed, digital to analog converters. I won't have time to go through, other topics that, we've been having fun with, in my research group, but feel free to take a look at our group website. They are relatively updated, so there you're gonna see that we have a lot of fun, working on a lot of high performance analog mixing, RF millimeter wave circuit and systems. So, okay, so let me get started. So let me first motivate, why we actually may use very high performance, D2A converters. So shown here, on the top, this is a pretty conventional transmitters, right? So you have a DSP, you go to the DAC, and you have a bunch of analog, post-processing, blocks, before you send to this final stage, which is typically a power amplifiers, before you drive to the antenna, right? So in this case, happen to be a wireless communication examples. And then if we think about this analog post-processing blocks, if for a moment, we think about if we actually bring this to the DSP domain, right? What does that mean by all this, filters, the fixed mixers, right? And another amplifiers and also another filter, right? So what that means is that, in the digital domain, the filter, you have digital FIR, IR filter, right? So you can easily build those filters and no problem. Amplifiers, right? Analog amplifier in the digital domain, I guess it's just a multiplier, right? You just multiply by a certain gain and you amplify the signals. Mixers in the digital, that's again multiplier, right? So you can build a digital multiplier, no problem. And then you can easily, multiply by any digital waveform, right, in the digital domain. So everything, if you move to the digital domain, it seems to be somewhat straightforward, to implement, in the digital logic, especially all this technology scaling, continue to benefit those high density, complex, digital functionality, right? So all that is no problem. But the little problem here is that, in the end of the day, we still need to convert that digital signal back to the analog domain, right? So what is that block, right? So that block, is what we call it as digital to analog converter, right? So this DAC, becomes, tremendously, important, in the context of this mostly digital transmitters, right? So all we need is this super duper, DAC, that's how I usually call it. So what is really this super duper DAC, right? So if you think about it, this is basically an arbitrary waveform generator, right? So as what I show you here, if you look to the market, if you ever, test in the lab, you probably have, use one of this equipment, right? So whenever you want to, synthesize or generate any arbitrary waveforms, essentially what you need is a DAC, right? So if you look at all this equipment that I show you here, they are super expensive, because the DAC designer, the high performance DAC designer is just not cheap, right? They are expensive. So I think that's partially explain why all this equipment are so expensive, right? So you need to really design a very good, DAC, with sufficient, speed, and especially in this case, you can see it's tens, hundreds gigasample per second, DAC, right? And you also want to make the signal coming out of this DAC, has high fidelity, right? So all that, add to the complexity, when you design this kind of DAC circuits. And also, a lot of those high performance DAC, they also design not just in CMOS, a lot of them, it can be in, 3-5 technologies, just to further boost up the performance. Okay, so this kind of vision of achieving a better DAC, higher performance, higher speed, kind of backdated over 10 years ago. So this was one of the first project I had when I started my research group at USC. We work with our sponsor at the time is the Navy, right? Sponsors, and they really encourage us to design really high speed, DAC with really high dynamic range, right? So this is what I show you here, right? So this is the typical DAC, territory, right? So in general, for the DAC design, you have two types. You have a Nyquist and you have a oversampling DAC, right? Which is usually known as a delta sigma DAC. And then if you look at the speed that this DAC operate and the SFDR, which basically, represent what's the dynamic range, right, of the signal that you can synthesize, right? And also typically when you design the DAC, SFDR is probably the most difficult, spec to meet. So that's why, I kind of plot this way. But then, bottom line is that, as you can see, the Nyquist DAC, give you a really good, speed and bandwidth. But you know what? The dynamic range typically is very limited, as opposed to delta sigma DAC, give you a much higher dynamic range, but the speed is usually limited. So if you want to kind of break the boundary, the question is that, what can we do over here in this territory, to allow you to hopefully, clock a little bit faster and also get a high dynamic range. Okay, so with that in mind, let's first review the two most popular DAC topology, right? As I mentioned in the previous slides, one is the Nyquist, the other one is the delta sigma DAC. If you look at the typical Nyquist DAC, usually they are done in the current mode. So what I mean is that, there's just a bunch of current sources, and then depends on the digital code, you would inject a certain number of the current into the output load, right? And that's it. That's usually what we call is the current mode DAC, or sometimes people call that as a current steering DAC. And because the current steering is very fast, so that become one of the probably the most popular way that people do in this high-speed DAC. Okay. But nevertheless, the bottom line is that, for the Nyquist DAC, you usually have a few elements, right? So in this case, you have a few branches of the current sources. And what you do is that, you just select a certain amount or number of the current branches, and inject the current to the output. So you can see you have a multiple current cell, and then each step, can be small. So that's the Nyquist DAC. And then when we move to the delta sigma DAC, it's really the other extreme, right? So you can see in the most extreme case, all you need is just one current source. Okay, so you just keep turning on and off this current source, but then you need to toggle that very fast, right? So that's why we also call this as an oversampling DAC, right? So you need to oversample this DAC a lot faster. So but then you just go on and off, right? This current. So there are different trade-off, right? So for example, I'm sure that many of you have designed analog circuits before, right? So whenever you try to design the circuit block that is more than one, right? You immediately worry about the matching, right? So that's one of the big issues. When you design the DAC, you have multiple cells, and if there's any mismatch, then it's gonna degrade your performance, right? As opposed to delta sigma DAC, there's nothing to match with because you have only one branch, right? So that's kind of the benefit. But of course, in return, it's hard for you to output a lot of power, right? Because you need to turn on and off, with a really, really large, step size. So that's generally, when you design the circuit, that will meet its own challenges. So that's kind of the trade-off, right? So how much power that you can actually deliver versus, how much accuracy you can actually, achieve, right? But in general, the delta sigma DAC does give you higher fidelity, right? So higher SFDR in this case. Okay, so one naive idea that we have been experimenting over the years is that we just thought that we should maybe combine the best of the two worlds, right? So you have this smaller step size, right, coming to the output, right? So that can be done in the Nyquist stack fashion. But then, you can still use that delta sigma, DAC concept, except that right now, as you can see, we try to modulate with a much smaller step size, right? So you have a large output swing that is, mainly delivered by the Nyquist, which you can roughly see there's a staircase right here. But on top of that, you have this little modulation going on here, right? It looks almost like a noise. Yeah, it looks almost like a noise. And that was actually, can be carried, by the delta sigma path, right? So we kind of, experiment this way, and we feel that, this may be the way that can give us both, right? So we can get the speed that we needed, and at the meantime, we also can get the resolution that we actually like, right? Remember that territory chart that I showed you? Yeah, so that's kind of the idea, behind all this, efforts, over the years. So this is what we call as a dual rate, hybrid DAC. Essentially, concept is very simple. You combine the Nyquist plus the oversampling path, and the way that you do is also quite simple. So you have the digital code coming in. You look at the MSB part, right? The MSB part of the digital code. So that you send to the Nyquist. Okay, the Nyquist path, and then you have multiple current sources that you would turn on and off. And then you take the LSB path and you send to the delta sigma modulators, just like a delta sigma DAC. And then you modulate, let's say one of them, right? Or just two of them of the current sources. So the combination is what we call as a dual rate hybrid DAC. And as I mentioned here, the whole idea here is that the output power was mainly delivered by the MSB path, which is the top portion of this slide, and the accuracy, right? Whenever you need accuracy, that will come from the bottom half, of this DAC topology. Okay. So that's kind of the idea, and then it turns out that we can based on this architecture, we can do even better than that, right? Because remember earlier I mentioned that whenever you design the analog circuits and when you have a multiple blocks that you try to match to each other, that's where you right away worry about the accuracy, right? The matching between those blocks. So it turns out that, if we actually go for these dual rate hybrid DAC structures, what you can do is that, yes, we understand your Nyquist path may not be accurate, right? Because, you are supposed to deliver a lot of power to the output. But you know what? If we can somehow measure those errors, right? So let's say you have, 16, those current sources, and I know, okay, between all those current sources have this amount of errors. You know what? If you are able to measure those errors, what you can do is that, you can actually take that error and then inject at the input of the LSB path, right? And this, we can also consider that as somewhat some kind of a pre-distortion, or technique, right? But except that here, we only do the pre-distortion on the LSB path, right? Only the LSB, right? So once you do this, you can actually truly get the best of the two worlds, right? So the top hat, you just focus on your speed, and you don't necessarily need to worry so much about your accuracy, right? How accurate you match those current sources, and you just let the LSB pad, which is the bottom pad, to worry about those design constraint. So based on that concept, okay, right now, yeah, apparently it's more than 10 years ago, right? So this was our first proof of concept, prototype. And then I want to show you this layout, and you can see in this red box right here. I just want to show you that that's where the current sources are, right? And that's it, right? So if you look at the entire architectures, that red box right there, that's the analog, quote unquote, analog circuits, right? And the rest, they are just digital, right? So that's really the beauty of this. I think is this dual rate, hybrid DAC, structures. You kind of confine, you kind of shrink your analog, blocks, right? So you make it very compact, right? That's also good because you can also make the matching also a little bit better, and when you do the clock routing, everything will be better, right? So I think this is another key benefit of doing these structures, and that's how we are able to push the performance, right? So let me show you some of the measured performance. This is the measured SFDR. So this is a single tone test. As I said, the DAC design, typically this is one of the hardest metric to achieve. So we get 91 dB SFDR. I think this one is at a little bit lower frequency. But if you move to higher frequency, in this case, I think this is at the Nyquist frequency, close to 500 megahertz. The SFDR is still decent. It was at 75 dB SFDR. And then if you compare to the state of the art at that time, right? So that was 2014. So at that time, we try our best to look for the open literature, right? The published one, right? I'm sure that there are also other good DAC that the people just never publish, so we don't know. But among all the published ones, we achieve, very encouraging, I would say very encouraging results, out of this dual rate hybrid structures. And by the way, just so that you know, the graduate student at that time, this was his first tape out, right? So the student actually has never done any tape out before, and that was the first one. And then when we were encouraged by the measured outcome, and not because we are necessarily a better analog circuit designer. I kind of attribute because the choice of architectures does give us some advantage, right? So it's not really we really that good to know how to do all this analog layouts and things like that, right? So I think that was encouraging. That was the first prototype that we have demonstrated. And then of course, we showed that to the sponsor. Sponsor was very happy, but then of course the sponsor always give you higher challenges, right? They say, okay, can you try to even widen the signal bandwidth, right? So you want to make the bandwidth even wider. So what we kind of go back and examine our architecture, right? So remember that because we do hybrid DAC structures, the LSB pad have this delta sigma modulation, even though we don't modulate very much, right? So the shape, the noise shaping, right? So if you actually happen to design delta sigma modulator before, there's always a noise shape. That's why you see this noise, which showing gray, it will start to increase at a higher frequency, right? So unfortunately, we cannot avoid that. But we do modulate just a small step, right? Remember that chart that I show you, the modulation is much smaller than the conventional delta sigma, DAC, right? So it's much smaller. So to begin with, you already talking about a much lower noise because of the delta sigma modulation. But there is still some, right? The bottom line is that there's still some, no matter how small the energy that we try to suppress it, it's still some. Okay. So what do we do, right? So we look at this for this our second attempt to improve this. We look at this and say, hey, you know what? What if I want to double the bandwidth, right? So before we achieved 500 megahertz in the first prototype. So what if I want to double it, right? What if I want to push that to 1 gigahertz? So we actually came up with this so-called in-band noise cancellation, right? So one of the beauty is that the delta sigma modulation noise is known, right? It's not unknown. right? So if you know that noise, so maybe you can do something to, suppress it. Okay, so that came to our second, prototype ideas, right? So we kind of look at the delta sigma modulators. We understand that, yeah, there's still a little bit of noise right there. What if I look at the difference between the input and output, right, of the delta sigma modulators? Then we actually know that quantization error, right? So that or that noise, right? So delta sigma noise, that's sometimes how people call it. Okay, so we know the noise, and which we can extract that noise only within the band of interest, right? So in this case, as I mentioned, we just want to double the bandwidth, so from DC to 1 gigahertz. So that's the band that we're trying to extract the noise, right? So this is very important, right? You don't want to cancel out the entire modulation noise, because in the end, then you do nothing, right? As if you remove the delta sigma modulator. So you don't do that. You only select the band that you really care about, the signal band that you try to synthesize. So select that band. So in our case, we actually use just a digital FIR filter, right? Just a simple FIR filters. We extract that band, right, up to 1 gigahertz. And so the output has 4 bit, and then so we kind of want to further compress that. So we actually apply another delta sigma modulator, in this case, the first order delta sigma modulators. So in the end, we just have a 2-bit output, right? So that 2-bit output, will modulate, this extra LSB current sources. We kind of use this to actually cancel out that noise, right? That I showed you in the previous slide. So by doing this, we found that, this is really an effective way to further, enhance the signal bandwidth of this dual rate, hybrid DAC, structures. Okay, and interestingly, what we found is that in the second prototype is that, remember how before I told you that, you can measure the errors from the MSB pad, right? So the current sources, they may have mismatched to each other. In the second prototype, when we are doing the noise cancellation, at that moment, we realized that, you know what? Maybe we can also cancel out the timing errors, right? So for those of you, if you actually design high-speed DAC before, or you are going to design high-speed DAC, the timing is very critical, right? So it's not just about turn on and turn off those current sources. It also depends on when you actually turn on those current sources, right? So the higher resolution that you're trying to achieve, then that timing control is a lot more important, right? But unfortunately, when we build the circuits, no matter how good we are, you always end up with some timing error, right, here and there, right? So here, it can be the delay, it can be a little bit more, right, or less. It can be the duty cycle, right? So sometimes you control those, simple, the current pulse, right, out. The duty cycle may not be exactly what you wanted. So it turns out that, we found that given this dual rate, hybrid DAC, your LSB, we know we do oversampling, right? So we clock at a higher speed. So we found that, some of those timing errors, you can also try to cancel it out, through the LSB. So that was pretty fun, so once we realized that, of course, we verified, in the summation, we saw that SRI is working. So that's why we carried that all the way, to the actual prototype. Okay, so this is the final implementation. As you can see, now we not only cancel the noise floor, but we also do this pre-distortion, right? And in this time, it's no longer just the mismatch between those current sources, it's also those timing errors, right? So the combination is the one that we actually, further push, for the second prototype. All right, so again, I show you this type photo. Again, the analog block is just this tiny bit, right? You see this current source right here. That's our analog circuits. The rest, they are just digital, right? And by the way, because of the time limitation, unfortunately, I cannot show you all the details. But if you are really interested in how we optimize this dual rate hybrid DAC, right? And how we, even cancel those timing errors. Fortunately, in this, I think in both cases, we do have this longer documentation. As you know, go for the journal version, right? So please, if you are interested, just read the journal paper. So there we actually provide a lot more analysis, right? And how we, find the theoretical bound, how we do the different trade-off, right? So yeah, so if you're interested, feel free to read that document, right? Okay, nevertheless, here, let me show you a few of the important measurement results. This is the one that I show you how effective that noise cancellation. Remember that we take the delta sigma noise and we extract the band, right? And you cancel it out. So this is before and after, right? So before cancellation, you can see the noise will keep going up, and that's because of that little delta sigma noise. And after you cancel it out, you can see the noise floor can go down a lot more, right? So that's just very good, as you are trying to expand your signal bandwidth. And again, we had no choice but to show the comparison with the state of the art. Again, I emphasize the published one, right? I'm sure that you may have your own non-published DAC result. All these are the published ones, and they're all from ISACC. And we again show that the performance again was somewhat encouraging, right? Okay, then then we show that to a lot of audiences, right? And also the sponsors, and at the time they say, okay, yeah, this looks like an interesting architecture, right? And so far we've been dealing with what we call the baseband operation, right? So it's always from DC to a certain bandwidth. And as you know, a lot of the communication system, actually most of the communication system, I should say, they always, since they actually use a particular passband, right? So Wi-Fi is 2.4 gig, as an example, right? And 5G, 6G, they have particular band, right? So the DAC that we are designing, not necessarily just, starting from the baseband. So the question is that, can you directly synthesize a passband signal directly, right? So then we're gonna go back and then we look at our structures and then we say, why not, right? So again, I'm showing you this dual rate, hybrid DAC, and we are not touching the top hat. Okay, the top hat is still Nyquist DAC. Okay, no problem. Just use your favorite DAC, Nyquist DAC implementation. But what we're gonna change is the delta sigma modulators in the LSP pad, right? So before, I was using the baseband version of the delta sigma modulation. And then if you happen to design delta sigma modulator before, you can always turn that into bandpass version, right? So what I mean is that, as you can see on the right-hand side, when you do the noise shaping, right? So you're gonna pass a signal at a particular band. So you can say particular band, you're gonna have the lowest noise floor. And then you're gonna shape the noise out of band, right? Out of that passband. So you can do that, right? So, and it's digital, right? So nothing is gonna stop you from even tuning that passband, right? So this is where, we think that, can go very nicely with a lot of communication system, right? Because a lot of the communication system, they do allocate this channel, right? So all the signal band was channelized. So you can hop between those channels. You know what? If you use this kind of a hybrid DAC, and then if you configure that into bandpass version, you can also hop those, right? You can select, depends which channel you want to synthesize, then go for it, right? It's digital configuration, and you can, hop to the band that you actually want to communicate. Okay, so that's kind of what we did. And this one just to show you, how you may, tweak that digital modulators, right? And depends on your settings, you can basically hop those channels. Again, for the detail, please just refer to our documentation. Just go for the journal one. That's a longer version of the documentation. And I believe that we actually talk about how we actually implement those. Okay. Oh yeah, so this one, yeah, we do have a journal version of this. And then look at this, right? The diphoto here, right? So the current source, again, is a tiny portion of the entire, DAC, right? By the way, I forgot to mention, all those digital blocks, we actually make a lot of redundant logic, right? So sometimes, just for debugging. So that's why the digital block may end up to be a little bit larger. When you make your own, product, you may not need a lot of those debugging capability, right? Because a lot of times we build those modes just because we can show to the community, right? When we submit a paper so that they can, people can understand a bit better, what's the effect, of various techniques. So that's also part of the reason why we have to make the digital logic a little bit bigger than what it need to be, right? So, okay. Again, there's some measurements, we show that, we can synthesize in this case, to be really wide bandwidth, right? So the DAC can clock up to 12 gigasample per second, and which will allow us to synthesize the signal all the way from DC to 6 gigahertz, right? So at that time, the reason why we choose this also because at that time there's a sub 6 gigahertz band, right? So the communication community, they are interested in the synthesizing the signal around this signal bandwidth. So that's why we kind of choose that to prove the concept. Again, the SFDR is good, and this is a two-tone test, right? Intermod 3 order also show a pretty decent performance all the way to very high frequency, right? Okay. And this one to show the noise spectral density, as we tune the different channel, right? Remember, it's all channelized and we can tune it. Yeah, so this one just to show, depends on which channel you are supposed to communicate. So you can always, lower the noise for that particular band. All right, so so the overall, I show you 3 different prototypes on this dual rate, hybrid DAC. There's a baseband version, there's a passband version, and I think, all in all, what really makes us excited, is this scalability, for the future, right? So that's why, every time I show you a DAC photo, I point you to the analog block portion, right? It's always small, right? So basically, we always try to, make the analog portion is small, and that's also the key for you to push for high speed. And then in return, yes, you do have more complex digital circuits, but we hope that, all the scale technology, right, or FinFET, that kind of devices can help us to implement more and more complex, digital logic, right? So that's sort of the trend, right, of this sort of hybrid DAC, structure, or I should say dual rate hybrid DAC structures. All right, so next, I'm gonna, switch a little bit, it's still doing the DAC, but I'm gonna, discuss, our recent efforts, to further push this DAC with higher output power, right? So in a way, if you look at the transmitter, right, remember that mostly digital transmitter that I show you, right? So you have a big DSP portion and you have a DAC, right? High-speed DAC. And in the end, you probably need a PA, right? The power amplifier to crank up the output powers. So what if you try to combine the DAC and the PA together, right? So in the community, sometimes people call that as a power DAC. If you talk to your RF colleagues, they probably see this as a digital PA, right? So to me, they talk about the same thing. So power DAC, digital PA. Okay, basically it's a DAC that outputs a lot of power, right? So okay, so in the second half of my talk, I'm gonna switch to this topic, just to see how we can further get that high-speed DAC, into a higher power region. Okay. All right, and then, the moment that I crank up the power of the DAC, something that will come into play, right? And that has to be efficiency, right? So efficiency has been something that, people always think about, whenever you design the power DAC or this digital PA, right? Whenever you design PA, efficiency is the number one thing you come to your mind, right? Why? Because, you're gonna consume a lot of power. You're gonna, emit a lot of power. So any power loss is significant, right? So that's why, when we bring the DAC into this high power domain, something that always come to our mind is always efficiency, right? So that's kind of our focus, for the second half of my talk. And specifically, what I'm gonna show you is the effort that we try to, improve the so-called backoff efficiency, right? So if you design for the communication system, most of the time, actually, your transmitter is not outputting at the peak power, right? You would, because of the modulation scheme, most of the time you are actually, operating in the backoff mode, right? So this is what usually people call is a power backoff efficiency or PBO efficiency. Basically, here I show you some of the Wi-Fi and LTE modulation. You can see most of the time they are operating not at the peak, right? Peak will be 0 dB. Usually you would back off, right? Sometimes, 6 dB, sometimes even 12, 13 dB, ish, right? So how efficient your DAC or your PA operate at that point is extremely important, right? Because most of the time your circuit is going to operate at that point. Okay. So over the past, I think probably almost 10 years now, right? we come up with this concept, we call that sub-harmonic switching concept, right? So we were very excited about this concept. So let me try to, convey these ideas, hopefully in a very concise manner. So we have this PA called, switching PA topology, so here, it's almost like an inverter, you just on and off, right? So this, is the switching PA, and we know that's very efficient. So whenever we want to, transmit, we just keep, toggling, connect this point to VDD or ground, and depends on, what's your input code. The more input code that you're gonna transmit, you're gonna have more, this inverter, to drive the output, to pull that to VDD, for example, right? So in the peak mode, right, during the switching operation, you always, toggle at the carrier frequency, right? So whatever that carrier frequency that you're trying to transmit, you just toggle at that frequency, and that's why, you can see a strong energy, right, show up at the carrier frequency FC right here. All right, so in the backoff mode, remember that we want to reduce the output power. So traditionally, what people do is that remember that the inverters, right? So they would just reduce the number of inverters toggling, right? So that's how people do. So our idea was that instead of doing that, why don't we just toggle all the inverter slower? How slow? So in this case, you can see we toggle at 1/3 of the carrier frequency, right? 1/3, exactly 1/3. Why do you want to toggle this at 1/3? So if you look at this switching waveform, right? So this is just square wave, and then the period, here is 1/3 of the FC. You know what? If you do a Fourier transform, what you're gonna see is that you of course you have fundamental tone at FC/3 right now, but if you look at FC at this point, you're gonna see exactly 9.5 dB lower energy, right? And what is that? That is exactly the backoff, right? Remember, in the backoff, that means that your output signal energy has to be lower, right? So in this case, it will be exactly 9.5 dB lower, right? So that's it. The idea is really simple. The so-called sub-harmonic switching PA concept is just that whenever you want to reduce the output power, just toggle slower, right? So that's what we call as a sub-harmonic switching PA. So the reason why we got excited is because we found that there's an additional dimension that you can do just by switching at different frequencies, right? And by the way, just so let you know, you can still combine with other power backoff technique, right? Doheny, class G, power basically sublime modulation technique. You can still use that. It's just that on top of that, you can have this sub-harmonic switching technique, right? You just basically toggle that slower, and then you can achieve the backoff, right? So that's sort of the angle, the potential opportunity that we've been exploring, right, over the past decade or so, right?
But that does put a higher requirement on the filter, right? Because you still have to meet the skirt of whatever standard you're trying to meet. I think it was 802.11b that you were showing. So does that not make the filter design much more difficult?
Yes, we can get back to the questions after the presentation.
Oh, I'm sorry.
No problem. No problem. Yeah, in fact, some of my following slides will already address that problem. Yeah. Okay. All right. So the spur is actually indeed important. But before I go to that, here are just a couple of charts to show you why the efficiency will be better just because you toggle those inverters, right, in a slower rate, right? So here is one case, this so-called conduction loss, right? So if you look at the conduction loss, through those switches, we know that, if you have them all toggled parallelly, right, the parallel resistance of those on switches will be lower. So if you calculate the math, you're gonna have 1/3 of the conduction loss, because of the sub-harmonic switching. Here's another example, where recently people have also been using the switch capacitor, right? So switch capacitor DAC, as a way to also implement the high-speed DAC. So this is just to show you if you have this switch cap array, as a DAC to do the digital PA. if you at the peak mode, right? So you toggle everything, you know, at FC, right? So at the carrier frequency. And then, you know, if in a conventional way, you decide to toggle only a few branches, right? So in this case, only toggle one branches, you're gonna have some charge loss, you know, because of the charge distribution through this capacitor array, right? So that's why you can see the efficiency chart, you know, you will go down, you know, if you kind of back off, right? The output power. So now, if you use this sub-harmonic switching PA concept, you can see we still toggle all the branches, right? So in this case, it's a capacitor branch, right? So you toggle all the branches at a slower rate because you toggle all of them together, there's no longer a charge loss on those capacitors. So you can see this efficiency will boost up, right, at that you know 9.5 dB backoff point, right? So that's another good reason why, you know, and how this you know, sub-harmonic switching can help you to, you know, reduce those efficiency loss, right? So in a way, what I'm saying is that, you know, when you do this, you can get the efficiency to be high. All right, so this is so based on that simple idea, right? Really simple, naive idea. This was our first prototype, and then we did that in the polar transmitters, and then in this case, you know, we use the switch capacitor array. And then just to drive this capacitor, you know, either to high voltage or low voltage, right? So we just ping pong between the two. And then, of course, you know, we implement this sub-harmonic switching logic. So you can see here, you know, we have one path, you know, coming at a higher rate, right, at the FC rate. And there's another path, you know, will come down to FC over 3 rate, so lower rate. So basically, we have a lookup table to decide when we want to which branch we want to toggle at the high rate and which branch we want to toggle at the low rate, right? So by doing those combination, you know, we can, you know, boost up the efficiency. All right, so that was the first prototype. So you can see we have this sub-harmonic switching logic. You know, it's just I think recently a smaller portion of the whole PA design, and that was done in 65 nanometers. Okay, so look at the performance right here, right? So this is the measured data to look at the efficiency, and you can see those some of the boost point because of the sub-harmonic switching. Okay, so I won't go through the detail of these tables, but you can roughly see basically the bottom line is that the efficiency is not bad, you know, compared to the state of the art. And then, you know, come down to a little bit related to that question, right? What about spurs, right? So you do generate the spurs. Do you increase the complexity of the filter, right? So yes, you know, if you don't do anything, yes, you know, you're gonna have a big, you know, spur right there. You know, you do need to, you know, redesign that, you know, output matching network, right? Just so that you can reject those tones. And another challenge, not challenge, opportunity that we were thinking is that, you know, in the first prototype, you know, we try to boost up at 9.5 dB point. Wouldn't that be good, you know, if we can boost up more point, right? So that's come to the second prototype. So one way to deal with that harmonic tones, you know, at the FC over 3 is what we call as a phase interleave, right? A sub-harmonic switching PA. So it's kind of like a time interleave, right? So if you design the DAC, sometimes, you know, you do use the time interleave, you know, DAC. So concept is a little bit similar. So basically, you can phase interleave these 3 branches, right? So if you want to, you know, operate at the peak output power mode, you know, you can combine the power, right? And you get the maximum power. So that's no problem. So that's how you should probably operate, you know, at the peak. But then, you know, at the FC over 3, so you back off, right? And then if you phase interleave, you know, the right way. So in this case, you know, you can see if you phase interleave at 120 degree, you know, offset from channel to channel, you actually cancel out the FC over 3 portion, right? The FC over 3, you know, harmonic, which is being the highest tone that you always need to worry about, it's just gone, right? So of course, you know, here I'm a little bit naive here. I just assume everything will match well, right? it will cancel it out. But in reality, there's gonna be a little bit mismatch. Yeah, so you still need to do something to balance it, right? To hopefully, you know, attenuate that FC over 3, you know, branch, you know, as much as you possibly can. Okay. So that's what's one idea, to deal with the tone issues. And then, we also found out in the second prototype, we can use more sub-harmonic frequency, right, to tackle this, right? So no one say that, you have to toggle only just one particular frequency like FC/3. You can also toggle it 2 FC/3, right? So if you do that, if you find out, those lookup table, those operation, turns out that you can also have another efficiency peak right here, right? So that's just another opportunity for you to further enhance, right? So this was the second prototype. You can see that we phase interleave 3, and then we also show how you can use that to further reduce that spur, right, at the FC/3. And then this one, I believe we do have a longer documentation. Yeah, so maybe if you're interested, you can take a look. I think we should have a journal version of this to document more details about this PA. Okay, so these are the measurements, just to show you that you have more efficiency peaking. And this one, oh yeah, so this one is the phase interleave. So you can see the phase interleave, we show that, at FC/3, how much that can improve, even without doing the filter, right? So without the filter, before and after, this how much that you can reduce. Here, I do want to mention, in our matching network, we do have an additional trap to trap out, to actually attenuate FC/3. The reason is that, here in the end, there's still gonna be some mismatch, right? So the more blocking ability, at those spur frequency is always good for you, right? So that's kind of address, go back to the audience questions. Okay, so this is a comparison chart. I won't go into details. So basically, it shows that the performance is not bad. Oh, and also in this prototype was the first time we pushed to watt level, right? So the output right now is watt level output, because now we have 3 branches. So we can combine in the peak mode, we can combine the power much better, right? So here, we actually can get the watt level output, PA. Okay, so later on, we have a lot more prototype. In total, we have 4 different prototypes, as you can see, span from RF, to millimeter wave. And I don't have time, unfortunately, to go through each single one of them. But here, just the chart I want to show you is that, if we compare it to all the state-of-the-art digital PA, right, the efficiency is not bad, because of doing this, sub-harmonic switching. Okay, so I do have one last topic. I was hoping to kind of show you more. So this is a result that we just present last month. So this is still very fresh. We present in ISACC last month. Still, the effort to increase the signal bandwidth of this sub-harmonic switching PA. But I understand that my time is very limited. So what I'm gonna do? I'm gonna just maybe pick a few important points, throughout the slides, and pardon me that I may flash through, with some of those slides. Okay. So this most recent prototype that we did was recognizing the fact that before, as I kind of show you before, right? So the initial prototype that we have been doing this sub-harmonic switching PA are using polar. So it's a polar structure, right? So you have an AM modulation, you have PM modulation. And when you do this AM and PM, this conversion, a lot of times people use this codec, right, to convert this IQ information into the phase information, right? And that conversion is very nonlinear, right? Because it's a nonlinear operation to find out the amplitude and phase. So we have this so-called bandwidth expansion issue, right? So basically, you clock your digital portion, at a certain speed, but the certain usable signal bandwidth is just a tiny portion, right? I mean, smaller portion, right? I shouldn't say tiny, just a smaller portion of the whole, bandwidth. So because of this, it's a little bit difficult, for us to, push the signal bandwidth, if we continue to use the polar structures. We do have other option, you can go to IQ. So basically Cartesian transmitters, right? Just I and Q. And still you can do sub-harmonic switching, no problem. But the issue here is that, as you know, when you do IQ, the combination is not coherent anymore, right? So you see you cannot have the power loss, just because you combine the IQ, you see the diagonal is only square root 2, right? So your energy is not combined, in the same direction, and then that's why you have 3 dB loss. So that's why the efficiency cannot be as good. What we may so the question that we kind of ask ourselves is that, can we do something better, right, to actually improve, so that we won't have a bandwidth expansion, and yet the efficiency won't be far off from the polar, right, structures. So this is our most recent efforts, right, we just presented. So we call that as multi-phase sub-harmonic switching transmitters. You can see here the idea is somewhat simple. So you still have a 2-channel, right? So we call it channel A and channel B. And what you do instead, instead of IQ, right, you have just 0 degree and 90 degree. Here we have a set of the phases, right? So in fact, here we have 8 phases to choose from. So 0, 45, 90, and so on and so forth. So whenever you try to transmit a symbol, you just select the 2 most relevant phases, and you use those 2 phases to configure the channel A and channel B, right? So as you start doing this, so what we found is that this multi-phase sub-harmonic switching PA, the efficiency will be closer to the polar, right? So the shown on top, this black is still the polar, so that's still the best. The blue will be closer, but it will be much better than IQ, right? It's basically the IQ structure. So that's the whole idea of doing this. So this come to the version that we had for the most recent prototype, and we try to achieve a very wide signal bandwidth. Of course, I won't go into the detail, but I think I guess one thing I can point out, since we spent so much time today to talk about the dual array hybrid DAC, and that's exactly what we did. You see this dual array hybrid DAC. So this is the first time we combine the dual array hybrid DAC, structures together with the sub-harmonic switching. And now, of course, we have the multi-phase. So we combine all the, techniques together. Why? Because in this case, we can achieve high speed, we can achieve high resolution, right? High dynamic range. And also we can hopefully achieve high efficiency, right? So here, it's really the demonstration that we're trying to see, what is the boundary that we can actually push all of those, metrics to be as high as we possibly can, right? Note that, we are doing research, so we don't have any particular standard in mind necessarily, but we just try to see, what's the bound, right? What's the boundary that we can push all this. Okay, so this is a diphoto. So you can see there's a channel A and channel B. And these are the measure the efficiency. So you can see we do have a mode where we can toggle between the quadrature mode and the multi-phase mode. And then you can see the multi-phase mode here, I believe should be on the right-hand side, right? So you can see this efficiency compared to the left side, which is the conventional quadrature mode. You have the fairly significant improvement, right, between these 2 structures. We also have some sub-harmonic switching suppression technique. Unfortunately, because of the time, I didn't show it. So they will be related to the audience question, how do you reduce that spurs? So we will, document this in the journal also. So hopefully in the future, we're gonna, show you how all those theoretical bound should be. But for now, if you look at our conference version, we already show you how we actually did it, right? How we actually reduce those sub-harmonic components. So you're gonna see how we actually do to improve the attenuation of this sub-harmonic point. All right, so here's another measurement on the modulation test. So you can see EVM about 30 dB, so 256 QAM, and these are the charts. I won't read this. Maybe I'll just show you this. Okay, so this is the chart that I show data rate versus the EVM and data rate versus the efficiency. As you can see, as you are pushing for higher data rate, EVM cannot be as good, right? Your efficiency cannot be as good, right? And then by doing this kind of combination of different ideas, we show that, you can maybe, start to break out that boundary a little bit more, right? So that's the whole ideas. And unfortunately here, we just have a conference version, and hopefully in the future, we have a journal version for the more detailed documentation. All right, so let me conclude my talk. So today I show you the dual array, hybrid DAC. It's really a structures that can allow you to do all kinds of, I would say, customization, right? You want to do baseband, passband, different channel, you name it, right? A lot of those are in the digital domain, so that hopefully give you some opportunity to do those customization. I also show you this sub-harmonic switching concept, right? So basically, you are adding one more dimension. Basically, you switch at different frequency, and in some cases, it buy you something, back, in the efficiency. Of course, there's always an additional spur that we need to worry about. So the question is absolutely valid and very good. So that's continue to be something that we can think about, to further improve it. Just like our recent prototype, we also did something there to further improve that, tones. And that's the multi-phase sub-harmonic switching. All right. So lastly, I know my talk from the very beginning was kind of driven by this so-called mostly digital transmitter, right? So I kind of use that as a driver to motivate, my group, my students to go for that. But it doesn't have to be that, right? So this is the last point I want to say. Even if in the future, right? So let's say 5G, 6G, I know California Dream, has a lot of emphasis on 5G, 6G, right? Even if you say, okay, I'm just gonna be happy with the analog transmitter structures. You know what? The DACs performance requirement, it will just become even more stringent, even if you use the analog, transmitter. So I hope that, whatever techniques that we're doing, right, even though, in the beginning, we try to be motivated through more digital transmitters, but I believe that, all these efforts to improve the DAC, higher speed, higher efficiency, higher dynamic range, will ultimately still, benefit our analog, transmitter structure, right? So that's all I want to say. Of course, in the end, I do want to thank all our sponsor, DARPA, SRC, and of course, my past students, everything that I've shown you today was not done by me, right? No way, right? It's all done by these three, incredible PhD students. Some will be my past group member, and Sumia is my current PhD student. So I just owe a lot of, gratitude, right? So a big thank you, for them, to actually, show all those fun journey, right, on the DAC. Okay, so I think I should stop here, and I have only 3 minutes left, right, I guess, for the questions.
Thank you, Professor Mike. Right. And this was a really interesting, great talk. Let's go to the questions. Any questions? I think Riaz had a question, and I hope Mike was able to answer your question.
Yeah, thank you.
Sure. That's a great question. Yeah, that's a typical question we always get, when people look at this. Yeah, by the way, feel free to reach out to me if you guys, let's say if you're interested, you happen to read our papers. If you have any further idea, how to further improve this, right? It can be a spur issue, right? As that audience questions. Feel free to reach out to me, right? So we can maybe continue the discussion. Yeah, and of course, for AJ, if the Dream Hub, continue to have interest, for those kind of high performance analog mixing or RF circuit, topic, right? Collaboration, I'll be more than happy to also collaborate, right? Things like that.
Thank you, Mike. So it seems there are no more questions. There is one question from David Cho from HRL. Do you know any of companies who are commercializing these DACs?
I'm not aware of any company for now. But I know the company have been interested in all this. So some of the company, they actually do set up some collaboration project with my group, right? So that's to the extent, if you are thinking about whether the commercial company are interested, yes, they are interested. Whether any of those company out there are already having a product, that I don't know. They, even if they do, they probably wouldn't tell me anyways.
Okay. So next week, our presentation will be given by, Mark Rodwell. It's March 28 from UCSB, Mark Rodwell from UCSB. It will mostly be on indium phosphide-based devices. So looking forward to that talk. And thank you everyone for attending this technical seminar series. Once again, thank you, Mike, for this incredible talk.
Sure, thank you.